Hello, everybody. Welcome at the 24th Getting Technical live event, and we are going to talk about productivity. But productivity in a different sense, because normally productivity is about how many work pieces per hour and per day and so on. What I want to talk about with you today and next time, because this is a two-part thing, is how can we reveal the secrets behind increasing productivity. And we are going to learn today and the next session that if we look at tool deterioration, that we can find a lot of data in tool deterioration and wear phenomena. And we are going to talk about those things. Today we are going to focus on what exactly do we mean with it? And why is there a relation between tool deterioration and productivity? The next session we are more going to discuss and talk about how to apply the things we are going to talk about today. Because today we talk about you analyze and stuff, but okay, how do you do it in practice? But that's for next time. Let's start with what exactly is it why is it so important? Because if you want to increase your productivity, you need data. Everybody talks today about data. We are a data-driven society in the meantime. And it's all very nice, but where do you find the data? And if we talk about machining, data can be found by asking the operator, but that's a rather subjective way of doing it, because an operator has a personal opinion about things. Or you can turn to cutting tools, used cutting tools, and there you find also data. And those data are more objective. Although objective, perhaps we have to be careful with as we go on in this presentation, and I'll explain a little bit more. What we are going to do today is trying, how should I say, to read a cutting tool, trying to observe how the tool is performing, and related to that, learn about deterioration of cutting tools and see the link between the two. And part of that is trying to recognize wear patterns, because I see it so often in machining. People are standing there staring at the cutting edge. They see something, and sometimes I wonder, they see something or they look at something, but do they see something? Because, you stand there, you see a used cutting edge, and then what do you learn from that? And that is what we are going to do today. As always, I'm not alone here. I'm together with colleagues, and in the background, they take care about all the technicality. And today we have a new kid on the block. Emma joined the team. Welcome, Emma. And let's continue here together in this. If you talk about tool deterioration, you need knowledge. And knowledge, where do you find knowledge? Knowledge you find in books. And I would say if you want to work with tool wear and tool deterioration, it starts with having the necessary knowledge, and that's available. You also need to know how to measure things, so you need something to measure. It can be the old-fashioned style, or it can be the digital version of today to measure things. And you need equipment to observe, because cutting edges are rather small things, so a magnifier glass, the traditional type or the digital type, is also part of the equipment you need. So knowledge and equipment, and knowing how to use the equipment, that's a must-have. And if we talk about tool deterioration, today I would like to do the opposite way of what people normally do, because people normally, they focus on wear, and wear leads to deterioration of cutting tools. And one element in the deterioration is tool life. If you have too much wear, you will have reduced tool life, and people struggle with that. What I would like slowly to do with you is to reverse that thing and start from the beginning by saying, to have a sustainable machining process, what tool life do we need? And starting from that, observing how tools behave, perform, and do they manage to perform long enough to be in line with expectations from tool life. With other words, normally people say, okay, when I do this and this and this, I have that type of wear, and my tool life is 10 minutes. And people are happy or unhappy with that, that's it. I want to reverse, I want to say, okay, I want, for whatever reason, 12 minutes tool life minimum. How can I make sure that a tool performs as such that I reach that level while the tool is still in working conditions, that the wear is not too big, that the deterioration is not at a too high level? And quite some subjects I want to delve in today with you, and the time is limited. So here and there I have to go very fast. But again, as always, this presentation is available. Just let me know and I can send you a copy, or we can continue the discussion after this live session. Because, first of all, today I want, of course, to respect the timing for this. So here and there we go a little bit fast, but let's try to do as good as possible. Now, if you look to small batch machining production today, and if we try to define it, one way of defining it is my way, perhaps a little bit, but I claim that small batch machining production is like a jungle. It's dangerous. It's unknown. There are things playing there we are not fully aware of. And, that has consequences. And consequences are that if you look to spindle hours, effective spindle hours, they are rather low. If you look to how cost structures are, and people still focus a lot on machining costs, but machining costs in the total picture in small batch production is only minor. We see that delivering on time is a big problem. People make all kinds of promises, and then after a while they start to realize, the promises cannot be kept for whatever reason. Non-conformity of workpieces, the quality is quite often a challenge. And the people working here is perhaps the biggest challenge of all. Now, all these things we are not going to delve in today. It's subjects we want to take care of in the next series of Getting Technical live events. But I just want to bring under your attention a bit that today's machining production is a bit like the equipment is there, the people are there, the machines are there, but the output is not there. It seems things are disappearing, and that's why I call it sometimes a jungle. Where do they go? And some keywords we have to remember when we talk about small batch production is variability. Things are changing all the time. You don't know in the morning what you are going to do in the afternoon. People are constantly on a safari trying to find something. There is a rumor it's there. Think on a cutting tool. There is a rumor there is a face milling cutter in the workshop. But where is it? Unexpected downtimes. The machine are supposed to run, but they are standing still due to events. And planning and scheduling, as I already said, delivering is quite a challenge. You make a planning, you schedule things, and after a while you realize, things are not happening as you thought they were going to happen. Now, if you, in such a situation, if you want to bring improvements, if you want to work on what people call excellence being better than your competitors in this, there are 4 chapters you have to focus on. One chapter is that you constantly should challenge the technology used in your machining processes. And that normally is not really an issue in machining. Sometimes it's even a little bit too much, I think. People are too much always trying to change things, and you have to find a balance there. It's also about balancing how you use your machines. Machines should be running as much as possible. That's what we call efficiency. On the other hand, seeing the variability in such a situation, you need spare capacity, and you will have to find a balance there. How far do I go with my efficiency, keeping a certain amount of capacity free for unexpected events? It's about uh, focusing on the unexpected. That's quite a firm statement. If it's unexpected, how can you focus on it? Yeah, that's the challenge. Unexpected downtimes, for whatever reason, should not happen. And you should focus on that, trying to find out why are things happening sometimes. And the fourth thing is, and it's a must-have for all the three others, that is that you have a team of machining people that are knowledgeable, skilled, but also flexible and multidisciplined. And that are the four chapters. Today we are going to focus a little bit on all four, because we'll see that used tools, they are somewhere in the middle. And if we talk about tooling and wear and so on, something that instantly pops up in people's mind is costs. Tools cost money. On the other hand, of course, you have the tool supplier saying, yeah, but tools cost money, but that's only a few percentage of the total. Now, I would say be careful with that, because in small batch production, with all the features, all the properties I already mentioned very fast, if you really delve into costs, and what you see here on the screen is just a typical example. It's not a rule, it's just an example. But in this example, what we found out is that tools costed 4 or 5 times more in the total cost picture of the company than what everybody thought. Then, of course, is the question, why is that? What's going on there? So that is one element we have to be aware of. Another element is that in small batch production, next to the direct costs, you have a lot of indirect costs related to tooling. If you don't have the necessary knowledge, if you don't have the necessary information about tooling, you are going to misuse the tooling, and that is going to lead to higher costs. If your tools are not in a good condition, if maintenance has not been done well, your tools are going to not deliver what you expected for. Again, extra costs. If you know the tools are there, but you don't find them, so the operator is out on a safari trying to find the tools somewhere. In the meantime, the machine is standing still. Again, a hidden source of costs. And you know, and perhaps this is the reason why tools in the end cost more than expected. You have the directly measurable costs. Your purchasing budget for tools, that's a cost. But next to that, you have a lot of other things playing in the background. And again, finding that is about observation. It's about looking at it, analyzing the situation, seeing what's going on, trying to find relations between things, and that's what we are going to do here. Let me start with tool deterioration. It's a term I always use because I think it's important to widen the notion of wear. Tool deterioration is a phenomenon meaning that something is losing the ability to perform in line with expectations. And important is to realize when we talk about a tool, a cutting tool, a machining process, that deterioration can be a physical thing. A tool is wearing out, due to that it's losing the ability to cut. That's physical deterioration, but it can also be, and stand with me here, because people, they think, ooh, now we are going strange ways. It can also be psychological deterioration, because if you have an operator and he's using a cutting tool, but the thing is not doing what he thought it was going to do, that's going to trigger things in his mind. And you see the picture here behind me. It's a road with deterioration. And if you have a car on such a road, this deterioration thing is not so good for the car. But this deterioration thing is also going to influence the behavior of the driver. And that's what I mean with you have physical stuff and you have mental stuff going on if you talk about deterioration. And deterioration as such gives people in manufacturing serious challenges or problems, whatever you want to call it. Because if a tool is deteriorating, it means it's losing its ability to perform, to do what you thought you wanted to do with the tool. And that is going to reduce the functionality of the tool. That's going to influence the quality of the finished workpieces. That's going to endanger the quality of the process itself. The process will become unstable. So, tool deterioration, it's not just about understanding what it is. More important is to control it, to manage it, to stay on top of it. And that brings me to why is this so important? Because the tool deterioration, in whatever form, we will define in a couple of minutes the different forms of deterioration we could work with. Tool deterioration is going directly to impact of operational efficiency. Because you made a planning, you thought this and this and this, and that planning you made in supposing that everything was going to function well. But if over time a tool starts to behave differently, that means that your efficiency is in danger. So tool deterioration and high efficiency is only possible if you manage your tool deterioration, if you control your tool deterioration. And for that we need to understand the effects. What are the factors leading to deterioration? Which factors lead to which type of deterioration? What's the relation between things? And that is what I call managing your tool deterioration. It's understanding a relation between tool deterioration and operational efficiency, but it's also understanding internally kind of the variables, the factors that lead to deterioration and in which way, what exactly the relation is. It's a rather complex process, I have to admit it. To put it like this, for me personally, I can say it's 50 years if I include schooling and so on. It's 50 years I'm in machining, and tool deterioration still has some secrets for me. There are, but I explain directly what I mean with this, and especially if you are in small batch production. That jungle, as I called it, because if you use a cutting tool always with a cutting speed of 200 meters per minute, after a while you start to know by observing that with 200 meters per minute you will have that type of wear, and it will lead to that tool life. And if that tool life is no good, you can loop back and modify your cutting speed. And that's what people do in mass production. But in small batch production, in the morning you machine steel, in the afternoon stainless steel, and in the morning you use a cutting speed of 200 meters per minute, in the afternoon in stainless steel 150 meters per minute, and by the end of the day you see a used tool. Yeah, and what is the relation then? You have been machining with one cutting edge two materials, and you have been using two sets of cutting conditions. So, what's the conclusion of what you see? And one could say, yeah, but you should not do that. You should use in the morning one cutting edge for the steel, and in the afternoon a second cutting edge for the stainless steel. But then the question is more economical. Because the cutting tool in the morning used was not fully used out yet. You could do more things, yet you decided to put it in the recycle bin and take another tool for the afternoon's job. That's a bit of a waste of money, isn't it? So it's complex, and you can have two attitudes towards this. There are two approaches possible if you want to master tool deterioration. One approach is what I call the passive approach. A passive approach is like your own performance. If you have a headache, take a pill. It's a rather passive approach. Translated to tool deterioration, if you have too much flank wear, reduce the cutting speed. No questions asked, just take a pill. That's a very passive approach. That's the people, working with the tables or digital form of a table. I have too much flank wear, what to do? Yeah, reduce the cutting speed, use a harder carbide grade, take a pill. That's passive. Active is trying to figure out what's going on, curing the disease by means of speaking. I would, from here on, want to continue with that active approach. If you observe something and it leads to behavior of a cutting tool which is for you unacceptable, that it's not about take a pill, but that we try to figure out what is causing it and what can I do fundamental to make the situation better. Now, there is some science behind this, very short. Again, if you want to learn more, this is where to turn to. Very short here, I have to keep my eyes on the time. Tool deterioration and wear. Tool deterioration is a phenomenon. It means losing the ability to perform in line with expectations. That's deterioration. Wear, which is one thing that could lead to tool deterioration. Tool wear is a progressive damage of the cutting edge. Tool wear is a cutting edge is in contact with workpiece material, and the two influence each other. There are all kind of physical things taking place there. You have abrasion, you have adhesion effect, you have fatigue effect, you have thermochemical reactions between the cutting edge and the workpiece material, and all of that is causing the cutting edge to wear out. If we want to understand wear, we have to have at least some insight in these physical things leading to wear. And also, very important, what are the variables, what are the factors influencing that physical phenomenon? And if you look at the cutting edge, a worn out cutting edge, and you see certain patterns of wear, some of the wear patterns we can explain if we know what abrasion is as a physical phenomenon. Abrasion is when you bring two surfaces together and they move relatively seen compared to each other, and there is some pressure and there is some temperature and things that the hardest surface is going to scratch away material from the softest surface. I don't know if there are physicians here in the people listening, and sorry then for this type of explanation. It's a bit simplified, I know, but let's call it a scratching effect. It's like with fingernails, you scratch your hand and you create abrasive wear. This explains a lot, but as you see, the blue circle there is not closed. There are some things we still do not understand. Another phenomenon is adhesion. Adhesion is a physical thing that makes the two surfaces connect to each other, and that's not really the big thing. The big thing is that connection, after a while, gets broken. And that breakage is damaging surfaces. That's another phenomenon leading to wear. And as you see, the green circle is not closed. We can use this to explain something, but not everything. A third phenomenon is fatigue. If you have two surfaces pushing against each other, but not like this, kind of a clapping effect, that leads to fatigue wear. Little cracks are going to appear in the surface structure, little things are going to break out, and again you have damage of a surface. And that explains also part of wear patterns we see on a cutting edge. But there's also a bit of, physicians, they talk about the butterfly effect, the chaos effect. There are still, with these three phenomena, things that we see happening and we cannot really explain why and how. And those things, correct or not, but are all pulled on one big pile. It's called thermochemical interactions between a cutting edge and workpiece material while the cutting edge is cutting. Uh, there's still quite a lot of research to be done there, but I think, and this week I was so happy to see that still young people in universities, and you see here it's very very recent. It's a girl, Rebecca Lindvall in Lund University, who finished now a PhD on wear mechanisms, and kind of focusing on that thermochemical interaction. Because it's good that we recognize, or we think we recognize is that, but we want to do something with that. And it makes me happy because sometimes we think wear is something old, nobody is doing anything anymore with it from a research perspective. But it's wrong. Young people still have an interest in that. And those phenomena, lead to worn out surfaces on cutting edges. And based on what you see, and that's why you need this little magnifier glass, you can try to figure out what exactly was the main physical phenomenon leading to a certain wear I see on a cutting edge. And it's by trying to understand all the different movements and types of contact there are between the ship and the workpiece and the machine surface and a cutting edge. And the cutting edge, how it looks, the geometry, the material of it, and so on. Now, models describing that, there are quite a few. You have, of course, the traditional Archet model for abrasive wear, but there are also more and more developed. See the PhD thing from Rebecca. Thermodynamic modeling, energy dissipation models are being developed, and there are surface integrity deterioration models being used. So it's a mixture of different models we use to describe it. And if we look to tool deterioration, we can talk about two big things. One is aging wear. It's wear that appears on a cutting edge over time. And then you have the certain deterioration phenomena also leading to that the cutting edge loses the ability to cut. Let me say like this, if I try to make it understandable for you, if people getting older, their bones, their muscles are wearing out. That's aging wear. And when you are 65, you can't do anymore what you could do when you were 25. Yeah, that's age. On the other hand, also young people, 25, can fall from the staircase and break their leg. That also is going to limit their possibilities. A broken leg. It's nothing to do with age, It's something that happens. And in machining, it's the same thing. There are some wear patterns that come with time in cut, that the thing is being used, and other things happen suddenly. If we try to classify a little bit, there are 4 wear patterns, and I'm using words here most of you, I suppose, are familiar with. Otherwise, again, you can turn to this for in-depth descriptions. Crater wear, flank wear, notch wear, plastic deformation, and together with flank wear, perhaps some flaking, which looks quite a lot like crater wear, are typical things that are time depending. It's typical aging wear. And normally those are the things we like from a predictability perspective. Everything else you see on a cutting edge, shipping, cracking, is things that it happens. And it has not so much to do with time. It's more phenomena that appear during machining and that lead to a certain wear pattern. Now, if we look to wear in machining situations, I would like to start by asking you to broaden your view a little bit, because people are watching a cutting edge with a magnifier, trying to find out what's going on. But that cutting edge, which is part of an insert, or if you have a solid carbide tool, it's integrated in the tool. But you have the actual tool holder, And that is also part of the picture. And later on, I'm going to give you an example of what I mean. But if your tool holders, broadest, this widest possible definition, are not in a good shape, yeah, whatever your cutting edge is not going to perform well either, So, step one, if you want to manage tool deterioration, is make sure your tools are in good condition. That's the start. Data. I already used a few times the word data. If you want to master tool deterioration, you need data. You need to know the application. You need to know the workpiece material in which a cutting edge has been used. You need to know the tooling concept. Was it a stable tool? Was it an unstable tool? Was it interrupted cut? That type of stuff. You need to know the cutting conditions, of course, the cutting data. You need to know the cutting material. And last but not least, you need to know the cutting geometry, both micro and macro. It's quite a lot of things. But that's what it is. All these are elements, factors, variables in the toolware equation. And solving the equation, but if all factors are unknown, is a bit of an impossibility. So the more you know, the less you have to suppose, and the more accurate your predictions will be towards the future. Now, again, in small batch production, this is a bit of a challenge because these things will be changing kind of all the time. And that's why, but that is for the next session here, that's why handling these things in small batch production, we need to involve statistic thinking a bit also. We need to look at the biggest factor, the biggest common denominator in the thing, and so on. Of course, there's always the butterfly effect, the so-called chaos. But don't forget what people call chaos is no more or no less that something, even a small change in one of the variables, can cause a big change in the outcome. Avoiding chaos is knowing all the variables to the highest level possible. If you fill in some of them with I suppose, then you end up with chaos. Don't forget that every used cutting edge is one bit of data. Every used cutting edge is one bit or byte or whatever data. But make it valuable data. Make that you understand it. Because big data also must be good data. Otherwise, it doesn't really serve any purpose. A machining process and toolware, we already talked about it. It's two things are opposing to each other. You have the loads acting on a cutting edge coming from the process. On the other hand, you have the cutting edge having certain load bearing capacity, and those two needs to be in balance. And if they are in balance, you master your tool deterioration. You master your productivity then. That's what it's all about. Now, if we look to singular wear patterns, there are traditional 8. In every technical guide, in every book, in every app, you find 8. From top left to right, flank wear, crater wear, shipping, notching. In the bottom, from left to right, build-up edge, plastic deformation, cracks, both thermal and mechanical cracks, and breakage. And I make the big vague because I don't think breakage is a wear pattern. I think if these wear patterns go out of control, you end up with breakage. But as such, breakage is a consequence, not an initial pattern. But anyway, that's a bit my personal opinion. Now, understanding these things, these 4, flank wear, crater wear, notching, and plastic deformation, we can use applied physics to understand and master them. abrasion and that type of stuff. And these are the, how should I say, the easy ones, but also the preferred ones. We can control them, we can master them, we can manage them. The four other are a little bit more difficult. We need a different type of modeling here. We need some stochastic modeling, because these things happen at first sight at random, in a chaos way of appearing. But as I already said, also there are methods to bring some order in these things. And why all this? Because, I always like to use the example of the nail and the tire. You can think you are on top of everything, and then one single nail somewhere on a road is causing you a big problem. And that's why if you look to used cutting edges, you'll see quite a lot of them due to the nail, by means of speaking. And that's what we have to bring some order in. Now, just to give you a complete picture, because I say I like the active approach to tool deterioration. Passive, take a pill, is for me, that's an easy way out, but not really solving anything. But anyway, the passive way, if you have the 8 wear patterns again, it's possible to define which pill to take. Let me put it like that. If you have a certain type of wear, if you don't ask questions too much about why and so on, just I have this wear, I don't like it, what should I do? Well, there are standardized methods to find which pill to take. Reality, however, is sometimes a little bit more difficult, because if you look to cutting edges in reality, you will see different wear patterns all at the same time. And then what? You can't take all the pills. Then you need something more sophisticated, but that's for the second part of this presentation. And why we have different types of wear is because we have different contact conditions between the workpiece and the cutting edge. Pressures are different depending on where you measure it. Temperatures are different. And wear is pressure depending. Wear is temperature dependent. So if these two things vary along a cutting edge, of course, you will have different types of wear patterns finding on the same cutting edge. And this picture, this diagram, I could talk a day about. It's perhaps one of the most important pictures that illustrate some basic insights in how wear develops on cutting edges. It's very strongly temperature depending, and this in the book I refer to, this is a chapter on its own, this one single picture. I just want to bring it under your attention. Different types of wear can also be something else. Here you see 5 cutting edges. It's milling inserts, 5 cutting edges, 5 different types of wear. What can we conclude from this? Nothing. Because the reality is these 5 cutting edges come from the same milling cutter. And all 5 have been used on that milling cutter for the same time, yet we see very different types of wear on the 5 cutting edges. And this relates to the condition in which the milling cutter is. Because if the accuracy of the seats in which the inserts are put is out of order due to wear out of the milling cutter, unbalance, or the milling cutter had a crash before, whatever, you end up with 5 different wear patterns on a cutting edge. And then what? From a practical perspective, people in a workshop, they are going to change all 5 at the same time. Not this time this one, and this time this one, and next time the other one. It doesn't work like that in reality. It should be, from an operational efficiency perspective, a bit stupid also to do that. But this is a very typical example how the condition in which a milling cutter is, when it's an insert milling cutter, the condition of the milling cutter leads to certain things we see on cutting edges, which makes life difficult for us. Because if you see these 5 cutting edges, and if somebody says, what should we do? Yeah, what should we do? It's not so simple. I have been talking a couple of times about tool life, just to make things complete. tool life as such. And as I said here again, the traditional approach, it comes in the end. We should have started with it. What is tool life? Tool life is a pure physical thing. Tool life it's a consequence. If you have this tool, you use it with these conditions and with this data, you'll see that after X amount of time, called tool life, the tool needs to be replaced. That's tool life. That's how most technicians work. I do this, and then I look at tool life and I find a tool life. A better approach is to work with what we refer to as economic tool life. What is economic tool life? Economic tool life is that from the beginning I say, okay, I look at the operation and from an economical perspective, because don't forget that every machining operation has an economical target. You want to produce a workpiece with a certain quality at a certain cost within a certain time. That's what you want to do. Now, if you focus on that, and if you then say, to realize my objectives, I need a tool life of X minutes, and then you go back, which tool to use, how to use it, so that tool deterioration is as such that it doesn't interfere with the wanted tool life. That's working with economic tool life, which is the better approach in my eyes. That means that looking at used tools, looking at wear patterns, for me, you need to involve time. Because you see on top 3 wear patterns, and we could have a discussion, what is good, what is bad. But if you don't know the time the tool has been used, in this example, 5 seconds, 5 minutes, or 50 minutes, it's a bit an irrelevant discussion. Because if the cutting edge to the right is still working, despite the big wear, the deterioration level is still below what is maximum allowed, and you can manage that for 50 minutes, I would prefer that situation over the situation here in the middle. If you start thinking like that, that is what we refer to as economic tool life, economic wear patterns. With other words, it's making sure that the behavior, the performance of a cutting tool stays under control. You master it. You don't end up in a situation that the tool is performing out of specifications and you have no control over it anymore. That leads to a certain maximum allowed wear, deterioration, and that should correspond with a certain time. That is economic tool life, economic wear patterns thinking. And that is we have models for that. It's the good old famous traditional Taylor model. It's over 100 years old and it still serves its purpose very well from a practical perspective. Taylor, more than 100 years ago, took a tool, took a workpiece, put the two in contact with each other and started to try to determine the variables that needed to take into consideration to see how they influence wear and the time a cutting edge could cut without endangering the efficiency of the operation. Taylor even found out a mathematical approach to that. So it's not just we have insight, but we can calculate with it. Perhaps the most important factor in Taylor, a factor which has been overlooked for a long time, but that was for the sake of simplicity, is the one in the middle, the variation factor, the chaos factor. And Taylor already in 1907 said that solving this equation is from a mathematical perspective nearly impossible. You can only solve it, he called it, in a numerical way. Today we would call it in a digital way. So finally, after 120 years, we are ready to work with Taylor's model, data-driven. Once we can do that, economic machining is in reach. We can control a machining process also in an economic way, that it delivers the correctly finished workpiece in the predetermined time and at the predetermined cost. This very short, and I do realize that here and there I jump perhaps very far. I hope most of you followed. Again, see this for more in-depth information. Tool deterioration, tool wear. It's not the same. One leads to the other. Wear leads to deterioration, but next to wear there are also other things that lead to deterioration. And deterioration as such is one of the most, or tool deterioration is one of the most important things to manage, to master, if you chase manufacturing excellence, if you chase process efficiency. So if you say I aim for that, then there's no way around that you will have to make sure you are on top of tool deterioration. You can't leave it just to coincidence. It won't work. And in small batch production, especially, it's essential. If you want to go for efficiency, if you want to go for high productivity, despite that small batch production is a jungle, as I call it, operators are important for you. They will supply you data, but a bit subjective because an operator has his own sentiment about things. Used cutting edges are a much more objective source of information. But then you need to be able to read it and to work with it, so that after the analysis you can come to a synthesis. Knowledge is important. Already here, just to come to a conclusion here somewhere, if there are people now saying, okay, nice, this seems interesting, what should I do? How can I start? What's the first step? I would say the first step is knowledge. Make sure the people involved in this have the knowledge, have the skills to pull out the data out of all those used tools. That's the first step. The second step is, to establish a structured approach to analyze tools. In Seco, we refer to such a structured approach as a GTDA approach, a global tool deterioration analysis. Global means, in this context, total, not all over the world. It's global for the full process, for the full workshop, and especially when you do small batch production, it's crucial. Of course, there is all the literature available for you. Also there, again, if you want to have a copy of this presentation, if you want to have more information about all the technical literature which is available, especially this one on tool deterioration, just let me know, send me an email, put something in the chat here with the event, and I promise you I take care as good as possible on all your questions and requests. And let's see, we have some time left. If there are some questions. One question is, will this stream be on YouTube to look at it later? Now I have to look at my colleagues behind the screen. I think it's a yes. She says yes. So yes. It's available later on YouTube, and also in LinkedIn you can see it again. Another question, how can I order the book on tool deterioration? As I said, send me an email, let me know who you are in the chat, and I answer you how you can get your own copy of that book. Somebody, I suppose you saw it in the slide, what is OTD and what is OQD? In the machining world, we have lots of abbreviations, and we sometimes forget about to explain those things. OTD means on-time delivery. It's a key. It's a metric people use in manufacturing to measure how well you keep your promises when it comes to delivery time. QD is the same, but for quality, on quality delivery. Do you keep your promises when it's about quality of the finished work pieces you deliver? Most tooling people say tools are 3% of production cost, and I suppose, state 14%. What is correct? But both are correct. First of all, the 14%, you added things up very nicely. Again, this is just a typical example. Don't go around spreading that I said that tools cost 40% of your cost. It was a typical example, but I wanted to illustrate that there is a difference between that tools are used in very controlled situations. Think on mass production, where indeed the tooling costs and the total machining costs are only 2-3%. Or tools being used in, I don't know if I should say uncontrolled situations, but anyway, in uncontrolled situations like in the small batch production jungle, where due to all those things going on, your tools cost more than what you anticipated for from the beginning. One reason the more to be on top of those tools, to make sure you control what's going on. And then if the better you become in that, the more you will see that by means of speaking, the 14% goes in the direction of 3%. Psychological tool deterioration, please explain. If I call, I don't know, again, it's my own thing, But if an operator, after a while, is stressed or frustrated, or not only an operator, can also be a programmer or a machining engineer, is frustrated because the tool is behaving differently from what he thought was going to happen, I call that psychological deterioration. It's influencing the behavior of the one working with the tool. I remember, any cutting tool is only as good as the one using it, and if that one is frustrated, also the tool suffers from that. Is deterioration the same as wear? No, it's not. I hope I made that clear. Wear is damage that you find on a surface which was in contact with another surface after a while due to the relative movement of the two surfaces which are in contact at a certain speed of movement, pressure, temperature. That's what we refer to as wear. Wear is nothing typical for a cutting tool. Ball bearings, your car, a washing machine wear out because things are in contact with each other and there is movement. Deterioration is losing the ability to perform. You have a tool, you determine the cutting data, the cutting conditions, you start cutting, you thought the tool was going to be capable of machining 5 workpieces before the quality goes out of specifications. And that 5 workpieces is due to that the tool deteriorates. It loses the ability to deliver good quality. If instead of after 5 workpieces, you already reach a certain level that urges you to replace the tool after 4 workpieces, that's the moment that deterioration becomes an issue for you. So it's not the same. I did not talk about point wear. And then the conclusion is this not important? It's very important. But point wear is not a wear pattern. Point wear, if you talk about point wear, it's a wear localization. It's where the wear is appearing. And point wear compared with cutting edge wear deserves more attention because, like always, the point is the weakest part of a cutting tool. And if that weakest part is suffering the most from wear phenomena, that's a double up situation towards deterioration. And that will lead to spoiling money because you have to replace the tool. The cutting edge is still okay, but the point has been worn out so much that despite that the cutting edge is in good conditions, you still or you need to replace the cutting edge. So point wear, or the place where the wear appear, but that's something we are going to talk next time about. Not only which type of wear pattern do you see, but where do you see it? On the edge, somewhere far on the edge, close to the edge, on the point, that type of things. We have a couple of minutes left. Now questions start to come in. As you discussed on tool deterioration, can we increase tool contact time by analyzing the tool deterioration in an active approach? I'm happy. Can I ask for the... Yeah, okay. The one who asked that question, yes, of course. Leave your information that I know how I can contact you. And as I said, I promise you can have all the information you want in this respect. A copy of the presentation, information about the literature which is available, and so on. But seeing the time now, because there are still more questions, but the other questions I'm going to take care of later on in the comments, and I formulate the answers as good as possible there. And as I said, we can of course continue this discussion afterwards. The next session, 28th of May, is part 2 of this, where more in particular I'm going to talk about the GTDA methodology, because today we try to define what tool deterioration is. What is it? What is wear? What are wear patterns? We also try to understand the why behind it, or as I called it, the science behind it. Why do we see certain wear patterns? And I kind of promoted quite a lot, I think, that you do an active approach there. That you don't go for the easy way, take a pill, but that you do, if you observe something, that you try to find out what's going on here, what's the reason behind this, and what could I do to solve this if what I observe is conceived as a problem, to solve it in a more structural way than just take a pill. But that is 28th of May. I hope to see you back, to hear you back there, where we are going to discuss more in detail how can we make it happen in reality then. Thank you so much. If there are further questions, whatever, put it in the chat, send me an email. I'll make sure you have all the answers and all the information you would like to have. Thank you very much, and looking forward to end of May to see you in part 2.